Okay, welcome everyone to today's seminar. It's a pleasure to introduce today's speaker, Sean Follmer. He is currently an assistant professor here at Stanford in mechanical engineering, and his research and also his teaching revolves around the design of smart and connected devices, and he really works at the intersection between human-computer interaction and also robotics. And Sean really pushes the boundary of what interaction interfaces are. He worked, for example, on 3D deformable shape displays that, among others, enable long-distance physical presence if kind of two people want to interact with each other, but many more things, as you will see in his talk. And in general, all good designed interactive devices should somehow be intuitive and playful. And I think he really exemplifies that. And maybe some of his devices will be the future of next generation game controllers and other interfaces. About his credentials, so he received a Bachelor in Engineering from Stanford a couple of years ago, then did his PhD and master's degree at the MIT Media Lab. He worked at Nokia Research, Adobe Research, and he also received a number of awards for his work. And so, without further ado, the title of his talk is Digital Spirits in the Material World, Dynamic Physical Media for Interaction and Display. Sean, welcome.
Great. Thanks for having me. So, as Ingmar mentioned, I'm an assistant professor in the mechanical engineering department. I also have a courtesy appointment in computer science. And really, the work that my group, we're called the SHAPE Lab, Smart Haptics and Augmented Physical Interaction. And the work that we're doing is really trying to look at, how does the physical world and the digital world intersect? And how can we really bring the benefits from the digital world, dynamic computation, lots and lots of different capabilities to the physical world, and then bring the benefits of the physical world sort of more into the digital world. And so what that looks like is a number of different systems built on top of robotics and mechatronic systems, as well as using new types of sensing and actuation to embody digital information in the physical world. So today I'm just going to talk a little bit about some of the work that I did at the MIT Media Lab during my PhD and postdoc, as well as some of the new work that we're doing at Stanford. So I've only been here about a year so far, so some of the stuff that we're doing is still not yet published. So this is kind of the work that we are showing actually next week or the week after at IROS, as well as Human Computer Interaction Conference, WIST. But anyway, broadly speaking, I think, again, this notion of, I really like the Police song that has this, we are spirits in the material world. And so the talk today is digital spirits in the material world, trying to bring the digital into the physical. So to start with, I think, in the mechanical engineering department and generally in human-computer interaction in general, we think a lot about tools. And if we think back to sort of the origins of humans and look at our evolution, what we find is that tools, as well as our manipulation of tools, really is central to our ability to think. And so these are hand axes from hundreds of thousands of years ago that really shaped our ability to manipulate the world, as well as our ability to think about the world. And so this idea of embodied cognition, of really using the physical world as part of our cognitive process, has sort of recently emerged in psychology and cognitive science as a driving force, as opposed to sort of this notion of Cartesian dualism that we're separate from the physical world. But really, my belief is that we need our hands and physical objects in order to think. That's part of our evolution, part of the way that we sort of became so able to think about such complex problems, was through our manipulation and dexterous manipulation of objects. And so as designers, we also shape tools. And so for a long time, these are, for example, tools that are used for throwing clay on a pottery wheel. And I think for a long time, designers of tools were very good at figuring out how the form of the tool not only provides its functionality, but also provides understanding or affordances to the users on how they might use them. So for example, this curved tool on the side there, it's clear to me that as I press this into the clay, it's going to make sort of an indentation of that shape. And so when we live in the physical world, we have this really direct mapping between form and function. And so physicality not only allows you to have this connection and understanding of what one thing will afford, and so there's this whole study of trying to think about objects in terms of their affordances, which human-computer interaction has sort of taken, but also thinking about the physical world as a grounding for collaboration. And so when we think about design and we think about sort of traditional types of design collaboration, as well as education, we see pictures like this that sort of show an architectural practice where we have physical models that we're building, and the idea of these physical models is not only for us to better understand them, to better understand what we're trying to represent, but also to communicate to others. And so the physical world really has this benefit that we can have things, we can all see the same thing, we can all manipulate it, and there aren't these rules as to who owns the content, who owns the view, and who's driving. Really, we can improvise with these. And so when we think about more complex tools, designers have, over the years gotten very good at being able to create more complicated tools that allow us to be able to manipulate many parameters at once while attending to something else visually. And this goes back to this idea of affordances, which I mentioned before. So for example, something like a Canon SLR camera, here I can attend to the picture that I'm trying to take while I modify a number of parameters, but my attention remains on the scene, and then I can just use these physical controls to easily do this. And so basically for 100 years, from the beginning of the 1900s till around the end of that century, designers knew how to provide these physical affordances to create really powerful types of interactions and powerful types of controls for more complex tools. But I think the computer really changed all of this. And the reason for this is because computation is dynamic. So computation has the ability to do, a computer like this could run a million different types of applications. But traditionally speaking, we've had very limited means of input for the computer. So for example, the dominant means are, keyboard and mouse, or now touch interaction. But really and it's kind of amazing what we can do with these keyboard and mice. We can have this really high precision of pointing accuracy, and lots of people have studied for a long time, what is a really good pointing device, what is a very good input device, and it's very hard to beat the keyboard, in fact. But for many applications, keyboard and mice doesn't really make sense. And so are they the best input devices for every type of interface? No, but the alternative is having many different types of physical input devices for these different applications. And so this has kind of long been a challenge, and my belief is that because computation is dynamic and we can use computers and now mobile devices to do so many different things. I think the mobile phone is a really good example of this, where we use the same device to communicate with people, to surf the web, to play games, to take pictures. And as I said before, it has the same static physical form for all these different interactions. And so as we look at sort of this trend, what we're seeing is this convergence of devices powered by digital computation, powered by Moore's law, moving from the special purpose or specific purpose devices to more and more general purpose devices. And so we have now these devices with increased functionality, but what we're seeing on the other hand is that the use of the physical affordances, these special physical buttons or input elements that are precisely tied to the specific applications, are decreasing. And so what we see is the use of graphical user interfaces instead increasing. And so I think this is a real problem because, as I mentioned before, really graphical user interfaces can get us a long way, but they lack the sort of immediacy, the sort of dexterous manipulation that we have with our hands, as well as our ability to think very spatially about problems. And so what the work I've been working on both at the MIT Media Lab and now in the Shape Lab here is really trying to think about, could there be another alternative where we could have dynamic physical affordances, where we could have general purpose devices, but still have really rich use of physical affordances. So my belief is that we need computers that can adapt to us physically. So not only can they adapt the applications that you want to run, they can also adapt their physical form. And so at the MIT Media Lab with Daniel Leitinger and my former advisor Hiroshi Ishii, we created this system Inform, which is a 2.5D shape display where you can actually change the physical form to sort of map to the different types of applications that you want to have. So not only the content can be now physicalized, but also we can physicalize the interaction as well. So for example, if you want to interact with a 3D model, you can now have the affordances of digital clay and sort of directly manipulate it. But then at the same time, if you need to, for example, pick a color picker could sort of physically appear when you need it and then disappear when you don't. And so the idea is really to map the types of interactions that you need to the physical affordances that you want and be able to render those on demand. So that's the general idea of these shape displays, is to not only have basically a 3D printer that can print in real time, but the real important thing that we think is that not only can you have now a 3D model that's physical that can update in real time, we can also have these affordances and interface elements that can adapt to how you want to use them as well. So how might you use these new types of shape displays in a meaningful way? So before I talked about architectural models and sort of how we traditionally have had physical models to represent cities, and that allows us to both understand it spatially as well as communicate about these designs. And so with Tony Tane, we built a system called Tangible Cityscape, where now, as opposed to having a static model of the city, we can have a dynamic one. And we can render that onto the shape display. And so we can pan and zoom around a city, and then the physical buildings are represented in real time. We can go in and physically manipulate that city, but also we can view different types of data sets layered on top of that and be able to really have a rich, meaningful interaction with it physically, as well as we can all stand around it and see the same type of information. So I think this points to a potential for some really new types of interaction and new applications that can be sort of supported by this type of dynamic shape display. And as I said, it's really about merging the content as well as the user interface together in this new type of physical display. So a lot of what I looked at during my PhD was thinking about what are these dynamic physical affordances? How can we create these interface elements on demand and be able to adapt them to how we need to interact? So for example, we can do very simple things like create buttons and sliders and handles on demand. So for example, you can have one button that transforms into many, or you can resize them, and they're all touch aware. So obviously this has a somewhat low resolution, but we're trying here to think about what are the potential new ways to interact with these objects. Or you can have a button transform to a 2D touch selector, so you can have change between these input dimensions. And these physical affordances can also be context aware. So as I move closer to a button, it can expand in size. So there's a lot of interaction techniques that have been developed in the digital world, which we can now bring to the physical world. So this is sort of target expansion, like the bubble cursor. So inside of this space of these dynamic affordances, we can think about changing their shape, their size, their position and orientation, their color, their visibility, as well as the way that they feel. So we can render different stiffnesses or vibrations through this as well. And so what that means is that we can really create a new vocabulary for physical interface elements that we couldn't before, because now we can change them on the fly. So for example, we can also create physical affordances that constrain our motion. So for example, if we want to move an object on this surface, we can create these physical constraints that constrain the motion of it. So we can create these new types of interactions where you can only move your object in certain ways. So for example, if you want to look at a 3D modeling application, here you could have some widget to rotate the object along one orientation or scale it. And again, here you have this physical constraint to have a 1D slider, and you can move between these physical constraints. So if we think about in the graphical world on the computer, we often have these constraints of sliders or other widgets, but now we can have them in the physical world. And so here we can also then easily move between different types of interaction and different modalities. So we can have, as you saw there, a widget that can appear so you can select color or change it. So the other thing we can do is appropriate passive objects as dynamic affordances. So for example, we can have a physical object, and we can actually use the display to move those objects as well, and now make them physical. So for example, in this case, you have, I'll just play this again. So you have sort of a scroll bar or a playback bar. So as you push this marble in here, it gets moved along as it's playing back audio, but I neglected to plug in the audio. But we don't have to just use marbles. We can move lots of different objects. So for example, if you have your phone on this device and you don't really see that it's ringing, then we can actually move the device into your field of view. And so a lot of what we're doing is thinking about, now that we have this type of device, what are the new types of interactions that this type of interface affords, and how can we prototype these and test these very quickly? So you might be wondering what this whole hardware setup is based on. So here is the underlying hardware that Daniel and I built, and it basically uses a lot of linear actuators. These are actually motorized slide potentiometers used in mixing boards, along with these Bowden cables to create a denser surface. So this is something like $40,000 in parts, and weighs, I don't know, 200 pounds, and is like the whole size of this table. So it's obviously not going to we weren't designing this for, with the intent of, that this would be the exact technology that would, be in people's homes. Obviously, this is not scalable at all. But what we wanted to do was build this platform that would allow us to try out different types of interactions very quickly. And so now at Stanford, we're working on developing higher resolution, lower cost shape displays based on different technologies that could scale better. But really, this was more of a research platform to allow us to be able to think about that. And so, yeah, this is basically more about the details. So there's these actuated slide potentiometers, as I mentioned. And then above it, we have a projector and a depth sensing camera to tell where people are interacting, as well as project visual information on top of that. And then all of these are connected, and basically we then use OpenGL custom shader that renders this depth map that we then send over to the shape display. So it actually runs basically general purpose OpenGL application. So you can really use anything you want. So the other nice thing is that it's back drivable. So these actuators are used a lot for mixing boards, as I said, and so they've really engineered them to be very good for human interaction. So we thought a lot about how could we merge content with user interface, and how can we really create these new types of interaction primitives that would allow you to have these richer physical interactions. But another thing that we really think shape displays can really point to is sort of in the space of remote collaboration. So when we think about collaborating in person, and this is based on a paper that we, Daniel and I, wrote for WIST 2014. But when we think about collaborating in person, it's very different from when we collaborate over video conferencing. And so we have physical materials around us, we have sketches, we have physical props we might use, we have whiteboards, And we have this ability to look at each other's face as well as sharing objects and sharing sketches and directly manipulating them. So really we like to think a bit about it as in terms of, there's people, but there's also objects and tools as well as the environment around us. And so when we think about kind of traditional remote collaboration or video conferencing, it sort of looks something like this. And it's very hard to have that same type of rich physical interaction and collaboration when we're in the same location, when we're co-located. So what we were trying to think about is how can we support this type of rich physical collaboration while we're distant? And so what we sort of have tried to look at is using this notion of physical telepresence to support as well as augment remote activities. So the main concept here is that we can now use the shape display to not only have content and user interface, but we can also use it to represent the remote participant physically. So for example, their hands can be here on the display shown in 3D. And so not only that, but we can also have synchronized interaction across the distance with physical objects as well. So we can point at these different objects, but then we can also have shared physical objects that can be linked and manipulated remotely as well. But then I think even more importantly, we can sort of go beyond this one-to-one mapping where we can now alter their capabilities and sort of go beyond physically being there. And then finally, we can actually have shared 3D models that we could manipulate and physically deform on both sides. So, in this space of physical telepresence, I think, one of the really important things is this notion of spatial referencing. So we often use physical objects when we're collaborating to ground our conversation. And so now with the shape display, we can, capture the remote participant and then display them using the shape display in their color, and that allows them to, reference 3D digital information as well. And so I, on one side, can be pointing and spatially referencing in 3D, and that's all physically rendered on the other side. So the remote or the local user doesn't have to wear any headsets, doesn't have to wear a 3D display. We can have multiple people all looking at the same 3D information. And on the remote side, we could have this asymmetric setup where we could have two shape displays, or we could have on one side some touch screen which could then also be used to interact. So for example, here I'm on one side and I have this touch screen view, and then on the other side this is my collaborator Daniel, and he can reference things and I can see that as well. So now not only beyond spatial referencing, you can also physically manipulate objects at a distance. And so we can use this depth sensing camera, to generate the physical geometry of the remote person. And because these pins are actually physical, you can now manipulate objects at a distance. And so this is kind of a new type of telemanipulation that hasn't really been explored before. So you can actually sort of start to move things around, and this is what you would see on sort of the input space. So the remote user sees this. But what I think is really the most interesting thing about this is that you can start to improvise. So you can not only have the ability to really quickly move things around, and manipulate more complex objects, but also you can bring in any object. So you don't have to have your hands. You could bring in a bowl and put that there. And so all of the physics sort of you just get for free. And so I think that's where this is really different from other types of robotic telepresence, is now we have this shared workspace where we can actually start to think about manipulating things in a different way. And obviously, this has a number of limitations compared to the physical world. So all of these pins are only moving up and down, so you actually can't apply any lateral force. You can only apply a normal force to it. But it starts to open up some interesting things. So we can also have sort of two shape displays that we're sharing. In this case, we only have one shape display, so we just slice it in half, but this would work over a distance. And really, here you can bring in physical objects and they can be represented on both sides. And so you can have this shared workspace where you can have digital information, digital content, but also, the remote user or physical objects as well. And one of the limitations to this is, let's say you have this ball on one side. One thing that I mentioned is that the pins only have, lateral, can only move up and down. So you can't actually press a pin laterally. So you have this virtual ball on one side. So we have this brush tool that allows you to sort of just push objects, and we detect its position and orientation. So then once we have these, two representations, we can, have these synchronized objects, as I mentioned before, and that allows two people to manipulate the same thing. And this is obviously, was that the noise? No. Okay. Sort of heard that noise slightly before it all went down before, so we'll just be on the lookout for that. Anyway, my apologies. So synchronized interaction. And we can also have just moving the object but not representing the remote participant. And finally, this idea that I mentioned before of augmenting the user and sort of going beyond being there physically. And so, when we think about altering our capabilities, now we can actually start to do that at a distance. So how can we actually make it better for the remote user to be remote than if they were actually there, as opposed to just trying to create systems that bring you closer to what it's like to collaborate in person. So, inspired by, work of Stellark, where he adds a third arm, or also, this scene in The Ghost in a Shell, where you have lots of fingers, or, on a more practical note, the Da Vinci surgical system, where you can, slow down or get rid of jitter that a person's hand has. And so we can, start to change their output modality. For example, here you can now become transparent, have this sort of ghost mode, or we can transform the user so we can make them have really large hands or rotate their hands. So here, for example, you have this bowl and you're not, you can't really grasp that, but if you had bigger hands, you could. And then on the remote side, this is sort of what it looks like. So you can scale this view as well. So here you have really big hands and a small ball. You can also sort of replicate your hands. So sometimes maybe you need an extra set of hands. So you're working on this, you can sort of freeze your hands in one position and then still be able to spatially reference things. Or you can replace the hand with some other end effector or tool. And so, traditionally with robotic systems, you have like a set fixed number of different end effectors that you could have. But here we're using the shape display, so we can kind of render any type of end effector that we want. So you could, have a sort of a scoop or a claw or ramps or, kind of anything. So I think it's interesting to think about how this different, now that we have this shared workspace, this way to physically render things, now we can start to think about different types of interaction and manipulation as well. And then finally, we can have sort of these two shared shape displays and be able to collaborate at a distance and have shared content. And so obviously, when we were doing this, we wanted to have, it'd be great if we had two high resolution shape displays. So at the time, we only had two low resolution shape displays and one high resolution shape display. But towards the future, now at Stanford, we're building even higher resolution shape displays. And we're really interested to think about how do you collaborate at a distance on meaningful tasks, such as computer-aided design, architecture, or visualization. So quickly, just as I sort of showed before, we're using this depth sensing camera to then capture the remote participant's hands or any objects, and then we send that over the network, or if it's on the same computer, and then render that through the shape display. So it's actually a really nice mapping, because the depth sensing cameras give you this depth map, which is a 2D image with depth information, and that's the same information that our shape display takes. So it's kind of a nice mapping there. And we can have, in the bidirectional capture scenario, we use two shape displays and we can link those together. But there's actually still a lot of open questions for having two shape displays. And then we were for that remote collaboration setup, we were using this other system called Transform, which we built for the Milan Design Week, which basically has a lower resolution. And so, obviously at this time, you're sort of thinking, hey, this might be kind of interesting, but it seems like there's a lot of limitations with your current implementation. And I would agree with you. So, I think the current shape display hardware that we have is very limited, in terms of the resolution. But I think maybe more importantly, to think about this class of shape display, the actuated pin array, you're always going to have this limited degree of freedom, the 2.5D rendering. You can't have overhangs. You can't actually grasp objects, apply forces laterally, only up and down. And obviously it's not very scalable. There's also some issues in terms of network latency. Obviously in all haptic teleoperation, latency is a big issue, and this is still a problem here. So I think where do these limitations point? I think obviously some are inherent in remote collaboration in general, but I think generally speaking, the actuated pin array is one approach you could take to shape output, but I think there's a lot of different types of interfaces that we could create. So quickly, I'll just talk about some other form factors of shape-changing displays. So one is this project with Ken Nakagaki, who's a PhD student at the MIT Media Lab, that we had for, I guess, WIST last year or the year before. And so here, basically, the idea is, as opposed to having this 2.5D shape display, now we have this smart actuated line. And so we can use that to display information as well as have this direct manipulation as well. And we can use this for a number of different things. And so Ken was looking at, what is this design space of these actuated curve interfaces? So what do we represent with these new types of line interfaces, and how can we interact with them? And I think, again, the really interesting things are when we use these shape displays or shape-changing user interfaces to interact with the physical world around us, because that's something that we can't do when we have purely digital information, is to manipulate our world. And so we built two different scales. So one is this larger system that can change stiffness and shape. And then a smaller one, which is just 2D, so the other one is 3D, but is higher resolution. So these are these two different platforms, and basically it's very inspired by work in robotics on continuum actuators and snake robots. But now we're thinking about how can we use these to display information. And so there's, again, these two different setups, and they're connected over a network to a computer, which does all of the computation. And so we can think about having these mobile devices. How could this curve now transform into a watch that could then be unwrapped to sort of then transform into sort of a flat shape that you can interact with. And so here the physical form, again, is transforming between these different affordances that you might want to have. Or we can use the shape to convey information. So for example, you could have a shape-changing cord. So here it's more about affordances again, where you can have this lamp where the actual cord is changing. Or you could display information through it. So you could have, as you sort of smart tables that sort of express things. And so again, the idea is to think about what are the ways that we could use this in our daily lives. And then also finally, as I was saying, having this physical interaction with the world. So we could have these constraints where you could wrap this around your wrist or your arm, and then it can actually move your arm. So for example, you can have rigid parts or flexible parts, and then one person can record, and then you can play that back on another person. So I'll skip over these other applications, but see the paper for more details. And then quickly, I'll just talk a little bit about other types of mobile shape-changing devices that we've built, and that's one area that we're looking at now at Stanford. So I think obviously, when we think about computers, we think, oh, our desktop But obviously now we have more mobile devices. But again, as I showed in the introduction, we use these for many different things. So how can we have the physical form transform to represent these different types of interactions? So again, this is work with Lining Yao, who I believe gave a talk last year as well about a mobile device that could transform again between a bracelet to a cell phone, and it's all pneumatically actuated. This is a project with Alex Owal and Daniel Leichtinger thinking about how we could actually deform objects into the different affordances that we need and lock them in there. So it uses like granular jamming to lock the shape of these devices. So as opposed to the previous work where the computer is determining the shape, here the user changes the shape and that informs its functionality. So then at Stanford, we've been thinking about how can we merge these more radical shape-changing mobile devices with kind of more traditional mobile devices. And so we have a paper that was presented at CHI 2016 about this haptic edge display, which basically has all of these small actuators on the edge of a mobile device. So now, as for example, when you're scrolling through a book, you can feel where you are in the book, or you can have much richer tactile notifications, or you can sort of render these dynamic physical affordances again, like buttons or sliders, so here you can have a game controller, and you have the shoulder buttons where you want them, but not where you don't. And so this uses all of these tiny piezo linear actuators inside of this mobile device. And we're also interested in trying to figure out what is the ideal resolution of these devices, as well as thinking about what are other types of actuation technologies that could actually make this expandable. So we have a demo at WIST looking at using switchable magnet actuators that can basically change. They're only binary, but they only use power to switch between up and down. So you can sort of create keyboards where you can move the buttons up or down, or again, these type of tactile feedback on the edge of a mobile device as well. Another area that we're looking at the Shape Lab is thinking about virtual reality. And so a lot of what we've been doing has been thinking about how we bring the physical world the digital world into the physical world. I think virtual reality is really bringing us into the digital world. But one of the real limitations of that is now you can see all these amazing 3D things, but you can't actually grasp them, you can't feel them or manipulate them physically. So we created this low-cost wearable haptic device called Wolverine, which Inrak Choi is the lead inventor of, who's presenting next week at the IROS Robotics Conference. And basically, the main idea is that we want to sort of simulate grasping of virtual objects in virtual reality. And we render forces directly between your finger and your thumb to sort of support this precision type of grasp or pad opposition type grasping. And the kind of key cool thing is that we use these low power, low cost, and low energy brakes. So we basically essentially just turn on the brake when your finger gets to the right point, and then you feel this really stiff, rigid object between your fingers. So something like 100 newtons of force, which is more than most people can grasp. But other people have looked at these kind of dissipative haptics before, but the main problem is that you can turn them on really fast, but often you can't turn them off fast enough, so you sort of feel this very sticky thing. So you touch an object and then it's quite sticky to release it. And so we use these one-directional brakes. So as you apply force downward, then the brake is on, but you can actually move your finger up and the brake doesn't affect it at all. So that's kind of reduces the stickiness. Also on the low power side, we just turn the brake on for something like 10 microseconds, and then your finger force downwards actually holds the brake in place the rest of the time. So it's really low power, low cost, so we can have a small battery and run for many hours. So he's presenting that. Then in the last area that we've been thinking about is, and I'll wrap up now as well, is thinking about how do we move from computers, on our desktop, shape-changing computers on our desktop, I talked about mobile devices, but how can we think about sort of more shape-changing environments that can adapt to different ways that we might want to collaborate with other people co-located or do different types of tasks. So this was a system Transform, which you saw some of the hardware, but with Ludwig and Ken Nakagaki and Verge Khan, we thought about, oh, how can we have this transforming table that could be in our daily lives and sort of convey information to us, but also adapt its form to fit the different ways that we might want to use it. So it can, as you bring a device over to it, it can actually sort of support that device and move objects, sort of adapt to the environment that you need it to be in. And I think where this sort of points to is really in this notion of moving from ubiquitous computing to this age of ubiquitous robotics or ubiquitous actuation. And so I think, really as we think about today, a computer no longer looks like this. And the age of ubiquitous computing and the Internet of Things is really here. As we learned from our interaction with the projector before, there's a lot of computers in our walls and pretty much everywhere. They don't look like computers, and they're often not designed very well, but they are here. We can't deny that. And so computers don't really look like this, but in the future, probably robots won't look like this either. So this is the canonical view of a humanoid robot, and I think it's really interesting to think about where robots are going to sort of intersect with our daily lives and how they can be used to display information, augment our environment, and really not used in the traditional sense of mobility and manipulation, but instead as interfaces and displays. So we can think about these ubiquitous robotics at different scales. So we've in this talk talked a lot about the device scale, but I think it's interesting to think about on the body, furniture, or even an architectural scale. And so I think this is a really new and exciting domain, this notion of ubiquitous robotics, which really combines interaction design, robotics, as well as human-centered design to think about, how are these robots going to, become into our lives. And so we have two projects that I'll really quickly just show some videos thinking about these ubiquitous robots. So one is this project we're presenting in 2 weeks at WIST, which is a collaboration with some researchers at INRIA, thinking about how we could have lots of small robots that we can use for information display as well as manipulation. And so they're called Zoids, and they're these small robots, and now we have something like 40 to, in theory, 200 of them. We're trying to fix them all the time. But basically, and you can use them to now display 2D information that you can physically manipulate with. So these are just some simple examples thinking about how you could draw shapes and have kind of physical manipulation with 2D shape information. But we're really interested in thinking about them in terms of their use for information visualization. Trying to figure out how to mouse. Yeah, information visualization. So here you can have a line chart where you can move through that data set, or a scatter plot. So each robot can represent a point in a 2D data space, and then you can manipulate lots of them at once. But also sort of thinking about them in our environment. So how can they display information around us and sort of adapt to how we might want to interact, so they can sort of all swarm around an object. Oh, you got to remind me to water my plant or something like that. Or again, you could start to think about how they could move objects as well. And then finally, thinking about, on the body, how can we use small robots to display information and provide physical affordances on demand? And so this is a project with Artem Dmitriev and Cindy Cao from the MIT Media Lab that's thinking about these small robots that can actually move on your clothing. And so they use a set of magnetic wheels and another set of magnetic wheels on the other side of your clothing to actually move around on your device, or sorry, on your body, on your clothing. And so this is the mechanism here. You can see there's the magnetic wheels on both sides. And then Artem has worked a lot to think about how we can control these and do things like dead reckoning and have IR beacons to position them, but also thinking about, how can we have on-demand sensing? So for example, medical sensing, you can have this robot move around your body to collect different information when you need it. Or for interaction, you could have all these robots that, for example, if you want to play a game, they move to different parts of your body and they all have IMUs. So then we can do things like motion tracking. Or for example, they could have a display on them and sort of spell out things. Sort of haptic feedback, or have move a scarf on your body. So use this for more decorative purposes, or sort of a brooch that, as you get a phone call, it moves up and becomes a speaker or microphone. And so I think really what this suggests is really thinking about a new type of interaction with computers, with information, that again is very physical, mediated in the world around us, and really adapts to the ways that we want to interact with people and with information, as opposed to us having to adapt to it. So in conclusion, I believe that we need computers that can adapt to us physically, and that's sort of what we're working on at the Shape Lab. And so I'd like to thank my many collaborators, as well as the Shape Lab. So yeah, I'd be happy to take any questions. I think we have like 5 minutes. So.